All right, let's get going. So how many times have I said you guys get the better class? About 1,000. Today I completely screwed up on something I'm going to show you a little later, and I feel really bad. So if you have friends in the morning class, say, look, A, you'll be less tired, and B, it's a better class. Go to the afternoon class. Hopefully I'll do a little better this time. But anyway, so we missed last Wednesday. Sorry about that. Although I hope you guys enjoyed your snow day. I wouldn't say we got behind so much as the stuff that we're starting today is what's on the lab. And hopefully most of you guys got the email that I sent around this morning saying, hey, at least take a peek at the lab before you go in there. There's some people who don't look like they've actually arrived yet from the previous lab this morning, and they hadn't actually had the class yet that we're going to do right now, and they didn't have the best time on the lab, I think. I think they did fine, but it was a little more stressful than it could have been. So anyway, pay attention today, and then look at the lab before you get in there. Just glance over it, and you'll see what it's all about. So here is what we are talking about today. I'm going to make a couple comments on homework. I should say homework 2. I don't know why it says homework 1. A couple more comments on homework 2, which is due tomorrow night at like midnight. There's a lot of office hours this week, today and tomorrow. If you need to go get some help on it, hopefully you guys are doing all right on it. If you haven't started it yet, I would get up, go, and start it now. Don't. It's long enough that it's something you don't want to procrastinate too much longer if you haven't already started it. So hopefully you're doing all right on that. So I'll comment a couple more comments on homework 2. Then we'll do a little bit more on recursion. I wanted to show you a couple other little things on recursion, and then we'll do the Unix tip of the day. Unix tip of the day is coming a little later in lecture, and you'll see why when we get to the first, what I would say, new thing that you guys has possibly not seen before. This thing called stacks, which is stack is another type of data structure, and it's our first real data structure after the list. And we'll talk about that, and we'll go from there. Any questions on logistics at this point? No? OK. So this should say homework 2 as well, because I was losing it. Homework 2. There we go. I've made a couple comments on Piazza. If you want to make helper functions, especially if your functions are getting really long, if you want to make helper functions, go ahead. Just make sure you put them in the private section of your class for, say, the day event on the homework. A number of people have asked this. I don't have a problem with you making helper functions. They are not necessary for this class. But some of you might want to make, say, an expand array function. That's fine. If you want to do that, put it in the private section, and you can still call it, and no worries at all. But please do a reality check on whether or not the helper function that you actually create is worthwhile. If you're only calling it once, it's probably not worthwhile. If you are, if it breaks up the flow of your work and it's not, you can't really tell what the function's 100% necessary or 100% for, don't go and make a whole other helper function for it. Like I said, you can do them, but you don't have to. OK? And the whole point of helper functions in general is to break away work that you're going to do multiple times and to make the program a little more clear. OK? Just know that you don't have to do that. Some people have asked about hard limits on function length. Try to keep your functions less than 30 lines. If you can't, that's all right. I mean, we'll probably point out in the homework description or in the report you get that some of your functions are more than 30 lines. But don't stress about that. OK, how'd the lab end up, guys? Was it all right? All right. Seg faults and stuff. Oh, no, that's not good. Well, we'll figure it out. These are guys who hadn't had the class earlier today and went to go to lab. So anyway, a couple other things on homework 2. Let's see. It's due tomorrow night. If for some reason you do have trouble finishing it or whatever, email me. We'll work out something on a case-by-case basis. I mean, I'd like you to finish it, but I would rather you tell me that you couldn't figure something out than provide something that doesn't compile and is completely, not going to work because that's just not going to help. In the long run, we want to avoid those things. So that's that. All right. Other questions on homework 2? Yes?
Do we need to use the commenting technique above our comments?
Yeah, good question. So I have been chastised for not putting comments in my own code, especially for this class. And I should do a better job than that. I am not particularly concerned if you do your own sort of commenting. Functions generally should have a comment at the beginning before the function saying, this is what this function does. But that's about all I'll expect. I mean, if you get into the code and something doesn't really, or something might be a little confusing, put a comment in there. I mean, don't over-comment, certainly. But yeah, if you want to put something at the beginning of the function, that's great. That's fine. Yes? You do not have to comment on the ones you didn't write. No. I should have done that. That's my bad. Thanks. Other questions? That was the same question? OK. Yeah. All right. I'll try to do better in the future. Yes?
How many times can you provide?
So right now, I think the limit is 100. So if you're providing more than about 4 or 5 times, you should probably step back a second and say, have I tested my own code enough? So don't use provide to test your code for you. I mean, I think that's kind of the bottom line. You should use it if it gives you an error and says, oh, it didn't compile, or this was a warning. That's a chance where you go, oh, OK, I get it. But make sure you've done your own testing beforehand. Yeah. So we'll probably let you provide as much as you want. But again, it shouldn't be the way you do your testing. OK? All right. Other questions on homework 2? OK. Hope it's going all right. OK. So the next thing we're going to talk about, a couple more things on recursion. OK? I mentioned the other day this idea of taking the greatest common divisor. And we didn't actually do any code, but I wanted to show you a couple different ways of doing this that uses recursion. OK? Now, remember that the greatest common divisor of 2 numbers, OK, is the integer that divides into those numbers evenly and happens to be the greatest one of those. OK? So the greatest common divisor of 20 and 15 happens to be 5. The greatest common divisor of 30 and 15 would be 15, because 15 goes in 15 and 15 goes into 30. OK, we get that idea. There's a way to find out what the greatest common divisor is for a number. OK, and I've written one method on the board already. OK, let's walk through this. We're going to return an integer, which is going to be the greatest common divisor. I call that greatest common divisor brute force, right? Which means brute force generally means that we're going to check every combination possible, right? And in this case, we do. We check every combination until we find the one we want. We're going to input a few things. We're going to input m and n, which happen to be, in this case, the 2 numbers that we're going to be trying to find the greatest common divisor for, and some other number that we're going to call g for our guess, to guess what that number, to guess what it's going to be. Now, our first guess is actually going to be the lower one of the 2 numbers we pass in. There's no point in doing anything higher, because it won't go into the lowest one. So that's what we're going to do. All right, here's how this program actually works. If m% equals 0, in other words, the percent sign means what? Does anybody remember, or you've done it before? It's the remainder. Yeah, the percent sign gives you the remainder of those 2 numbers. So in this case, if we picked, let's see, if we picked 20 and 15 and then 15, what it would do is it would say, OK, look, if doing m divided by g gives a remainder of 0, 20 divided by 15, actually the remainder is 5, so it's not going to work on this one. And if n remainder g, divide and get the remainder, equals 0, then we've actually solved the problem, right? We return the value that is the greatest common divisor, as long as we start at a number high enough. OK? And that's all that this line's saying. Otherwise, we're going to return the brute force, the greatest common divisor brute force of the same numbers that we had before, and then g minus 1. So we're just counting down, right? We're going to start at 15, and then we're going to go 15, is it the greatest common divisor? No. And then 14, and then 13, and then 12, and then 11, all the way down to, as it turns out in this case, for this one, it would be 5, and then it would be done. OK? It is a recursive function. It's calling itself, and it's just recursing down. I have a base case here, which means we've solved it, and we've got the recursion. Everybody good with that so far, that part of the recursion? OK. Is this the best way to do greatest common divisor? Turns out that it's not. OK. There is another way to do greatest common divisor by this guy named Euclid. You might have heard of him. He's around about 200 BC, like over 2,000 years ago. And he said, look, here's a better way to come up with greatest common divisor. He said, for m is greater than or equal to n, which is greater than 0, the greatest common divisor of m and n equals the following. I'm going to get a little mathy again, just for a few minutes here. OK, equals, that's my terrible curly bracket again. When I was in 4th grade, I got a D in penmanship. That's why I was pretty sad about that, actually. Greatest teacher, that Miss Harder, she was a phenomenal teacher, right? Brings me up to the front of the class one day, not really in front of everybody, but says, look, I got to give you a D in penmanship. My parents bought me a typewriter after that, actually. They're like, forget it. It's not worth it. Anyway, for m greater than equal to n, greater than 0, the greatest common divisor of m and n equals n if n divides into m with no remainder. Right? And that makes sense. I mean, if we said the greatest common divisor of 30 and 15, well, it's going to be 15 if you get a remainder of 0 when you divide those two numbers. Or it's going to be the greatest common divisor of n, which is the smallest of the number, m% n, which is actually the remainder when you do m divided by n, right? And as it turns out, this works beautifully to find the greatest common divisor. OK? Why does it work? Well, there's a couple different reasons. Let me just show you briefly why it works. If you take m, you can rewrite m like this. OK? You can say m equals n times this funny function I'm about to do, m divided by n plus the remainder of m divided by n. This means the floor of m divided by n. Okay? What the floor means is do m divided by n. When you get that number, it's got decimal places after it possibly. Truncate those decimal places, get rid of them, and just return the integer value. So this is actually an integer. So if it was 20 and 15, 20 divided by 15 is like 1 point something, right? 1.3 or whatever it is, right? And what you return is just 1. So 20 divided by 15 is 1.333, whatever. The floor value of that is 1. So that's an integer, integer, and integer over here. So far, so good? All right. When you look at this, if d, say some other divisor, d divides into both m and n, meaning it's divisible into m and it's divisible into n, it must be divisible into this. Okay? Because if something times d equals n, that means that if something divides into n, that thing also divides into some other value times n if it's an integer. So far, so good? OK. So we know that d divides into this. Of course, d divides into this, m, as well, because we already said it did. That means that d will also divide into this remainder when you do m divided by n. Why? Let me show you. If we subtract, well, let's do this. Let's say this is d times a, because it's going to be d times some value. We know d divides into it. And this is going to be d times, say, b, right? Some value because d goes into this, we already said. OK? And I subtract db from both sides. We get dA minus db equals the remainder of m divided by n. If we factor out a d, a minus b, like that, right, equals the same thing here. Well, that means that d times some value has to equal that value, meaning that d will also go into this value. OK? Does that make sense? That's why we can actually say that this works. How would we actually write this? It's actually a pretty simple change to the actual recursion here. In this case, we're just going to call it GCD. We don't even need the brute force on there. In fact, I'll erase this whole part here. It's going to be GCD of m and n. Okay, that one was better. Curly bracket. All right. If our base case, which is if m% equals 0, right? If m% equals 0, return n. In other words, we're just returning the value that happens if m divides by n and gives no remainder. That is the greatest common denominator between the two numbers. Return n. Okay. Otherwise, we just need to return GCD of n or m% n, oops, which is the remainder when you do mn. All right, and that's the end of it. So it's actually a lot easier, and it gets to the answer much, much quicker. Okay, and you would be able to use this one and it'd be a little quicker. Can you do this in a non-recursive way? Sure. We could write a little loop that does exactly this without going through this whole recursion. And as I said, I think I said on last Monday, recursion is not some magic answer to programming. Sometimes it makes things look a little nicer and look a little easier, or look a little better, but it's not necessary. It doesn't do anything special. In fact, sometimes it takes more time to do some of these things. Okay? Question on that? No? OK. So that's about all I wanted to talk about for recursion. I mentioned the other day about doing recursion to solve the palindrome problem, and I wrote some code online. Probably not commented very well. I wrote some code online that actually goes through that whole the whole check of if a statement is a palindrome or not. So feel free to check that out. I think it's from last week's lecture. It's under there. Okay. Questions on that? On recursion in general or anything else? No? OK. So today's lab, why don't I talk about that for 1 sec while I'm erasing. So today's lab is actually partially on recursion, right? Part of the lab is going to involve recursion. The other part is going to be involving stacks, which we're going to talk about next, well, almost next. And it is, I think, a kind of a fun lab. Did you guys have fun doing it, the lab? It's kind of a fun lab. The lab is, yeah, they're like, yeah, we had a lot of fun working lab. The lab is actually about solving mazes, okay? And you guys got the email today about it, right? If you have a, Bruce is much better at drawing mazes than me, by the way. I don't know. I'm not very good at drawing mazes, but let's. That's a terrible maze. Hang on. At least maybe like I don't know, like there. I don't know. Whatever. Anyway, okay. That's a terrible maze. Anyway, yeah. So if this was the start, and let's say this was the finish. Aha! You thought the finish was going to be down here. If the finish is up there, right? This is whatever. I was also terrible at Anyway, the thing about a maze is that there's lots of different ways to solve mazes. Okay, one of the ways the way we're gonna do it in the lab today is called this thing called a depth first search, which basically means go through every solution and try everything you can to find the solution. And when you find it, you're done. If we are here, let's say we're here, and let's say this was like a little block, right? We're here. What directions can we go from here? We can go this way and down. So we can go like east, and we can go south if we're going to do this with like coordinates. We can also try to go north, and we can try to go west, but we'll hit a wall. But we don't know that until we try it, right? So the way you're going to do the lab today is actually go through and say start here and try going north. And if that works, like let's say you were able to go north and it ended up getting you to the finish, and there was some path that made it there, you'd be done if you try to go north and start that way, right? Or you try to go east, or then you try to go south, then you try to go west. And if you do that, and you do it recursively, in other words, every time you go north, then you try going north, and if that fails, go west and south and east and whatever, then if you keep doing that in the same pattern recursively, you will eventually find the finish, as long as one exists. Okay, you'll eventually find it. And that's the recursive solution to this. Okay, so that's part of the lab. You'll see when you get there. It's basically fill in the blanks on the code itself, but that's how it works. I'm gonna have to ask Bruce how he draws mazes. I missed that day in kindergarten or whatever. Okay, so let's go on. What I want to do is show you the Unix tip of the day. Okay. All right. There are two programs. One is called DC and the other is called BC that are on Linux distributions generally. And they're also on, if you have a Mac, they're on Mac OS X. If you go and you type DC down here, okay, it looks like, hang on, looks like it's not doing anything, but it's actually just sitting there waiting for input. Okay? I'm going to write something, and I'm going to see if you guys can figure out what it's doing. Earlier, I actually wrote something that was too easy. I'm going to write something that's a little harder. Not particularly hard, but let's just see. 4, 5 times 3 plus. OK. If I type that, 4, 5 times 3 plus, and in DC you actually do P to actually print out the answer, take a look at what prints out. 23. OK. Let me try something else. Let's try, what's that? Put the numbers first and the operator after. Yeah, that's actually pretty close to what it is. Has anybody seen this form before? Yeah, there you go. I've heard somebody say it. This is actually, what we're doing up here is called reverse Polish notation, or otherwise known as RPN, or otherwise known as postfix notation. Okay, the reason it's called reverse Polish notation, there's postfix and there's prefix. Okay, the guy who invented prefix happens to be Polish. A long time ago, he invented the prefix thing. When you switch it around and make postfix, well, you've reversed it. So this reverse Polish notation is what we're doing up here. Okay, so let me show you another one. Let's do one that says like 5, 3, 2 plus times. Any guesses on what's going to come out of that one? 5, 3, 2 plus times. If you don't know, that's OK. If you've never seen this before, this is like, it's crazy.
It's 30.
5, 3, 2 plus star. Well, let's look. It's 25. What? All right. 5, 3, 2 plus star. Here's what's going on. OK? 5, 3, 2. The plus has, how many things do you do when you do plus, right? There's 2 operands when you do plus, the plus operator. Those two, that plus acts on the 2 and the 3. And what's it give you? 5. And then you hit a times, and that's times goes on the previous 2, which is 5, and 5, which is times. Right? Let's look at another one. Let's look at 3, 4 plus 5 times 2, 6 plus times. 3, 4, let's see if I wrote it down. 3, 4 plus 5 times 2, 6 plus star. Yeah. Let's see what this comes out with, too. 280. OK? Let me show you what's going on here. All right. Let me write this down. 3, 4 plus 5 times 2, 6 plus times. OK. The way this works, as we saw earlier, is you take in a couple of numbers, and then if you hit an operator, you apply that operator to the numbers that you just saw. Okay? So we hit the 3 and the 4, and then this plus acts on the 3 and the 4, okay? And we end up with 7. Okay? And then you hit the 5, and you don't do anything, so it's just a number. Then you hit the times, and that times acts on the 5 and the 7. Right? So now we get 35. Okay? Then you hit a 2. I'll write it down here. Then you hit a 2. Then you hit a 6, and we haven't done anything yet. Right? Then you hit a plus. Okay? And the plus says, do that operator on the previous 2 numbers. The plus goes on the 2 and the 6. That gives you 8. And you're still left with 35 and 8. And then we hit the times. And then you do times on the 8 and 35. And hopefully, 8 and 35, 8 times 35 is 280. Right? OK, so that's now, you hit the times, and then you get 280. OK, do you see how that works? All right. It used to be that the first desk calculators you could buy, they call them desk calculators because they were like this big and they sat on your desk. They were about the size of a typewriter. Do you guys even know what a typewriter looks like? Probably too young for that. Anyway, desk calculators, a lot of them had this notation built in. So you actually had to learn this notation. It's not that hard. In fact, I have a calculator on my computer, the one right up here, that actually I use sometimes. And 5, 2 times, whatever, right? And it you can use those. And what's nice about this? Like, there's a couple nice things about this form, even though it looks weird to us. What two things didn't we have to know to do this form? We didn't need to know order of operations, right? No need to know order of operations, which is great. You just keep going until now. You have to know them kind of in your own mind when you're writing this out, but you don't have to. Like, the computer doesn't need to know anything about order of operations. OK, let's see. You also, are there any parentheses in here? No, right? No parentheses necessary. OK, so it's not a bad little form. OK, so that's the DC calculator. OK, all right. Let me show you the other one called BC, which stands for, I think, basic calculator or something like that. BC is for those of us who don't want to write like in postfix notation. We want to write like 4 plus 5 times 2 minus 6, right? We want to do it with parentheses and with order of operations, right? Actually, let's do it this way. Oops. Let's say times 6, right? That should happen first, right? So it's going to do 10 times 6 plus 4, right? Because we do have to know our order of operations. And in this case, this one does. So if you want a regular calculator that does that, you can do that. The cool thing, but that's not the cool thing about BC. You've all got calculators on your phones and things, right? What's cool about BC is it will do arbitrary precision, which means that I can do something like 1, 2, 3 raised to the 4, 5, 6 power. Boom, right? This is like a nice long number, right? Why is it so long? Because that's a big number when you raise 123 to the 456th power, right? That'll do it, and it just spits it out, right? It just allocates more memory as necessary. I'm not sure how, I mean, it'll 1, 2, 3 to the 4, 5, 6, 7, right? Yeah, it spit it, that's a nice long number, right? Okay, so it'll do it for you. Why not, right? So it does allow you to do that. The one thing you have to be careful with BC is it doesn't have a built-in precision for decimals. So if you do something like 10 divided by 3, you end up getting the floor value, which we talked about earlier, of 10 divided by 3, right? 3.33, it's just going to give you 3. So you can do a flag at the beginning of the command to actually get it to do decimals, but still, it's kind of cool. Okay, so if you want to calculate pi to 1 billion digits or something, you could probably use BC if you had the right formula. All right, questions on those two types of calculators built into Unix? All right. So the next thing we're going to talk about is the first data structure. Who here has heard of stacks before, besides people in lab today? You didn't do them in 11, though, correct? OK, or well, I don't know if you did it. You kind of almost did them in 50. I heard you almost did. Like something you did some things that were stack-like, but it doesn't matter if you haven't heard the name. Here's what this data structure is. Okay, it's a simple data structure, and it's simple for a reason. Even though it is simple, it's a very powerful data structure. Okay, here's what a stack, and it's so common. I'll talk a little bit about in a second about what's common about it. But stacks are extremely common, and here's what it is. Let's say that you have a plate, right? Like a plate for food, right? The nice thing about stacks also is that it sounds like the analogy that I'm about to use, right? Let's say you have a plate, and let's say you're going to have a plate of pancakes, right? And you throw a pancake on the plate like that, okay? And then you're a little hungry. You're kind of hungry, so you put another pancake on there. And then it turns out you're really hungry. You put another one on there, and you put another one on there, right? And so now you've got a stack of pancakes, right? How do you actually go about eating that stack? And most of us would just would cut down a big chunk here. And no, let's pretend you can only eat one pancake at a time, right? What you're going to do is you're going to eat this one, then you're going to eat this one, then you're going to eat this one, then you're going to eat this one. But which one came off the griddle first, right? This one came off first, okay? Stacks are based on this principle of last in, first out. In other words, the last thing you put on a stack is the first one that gets taken out, okay? So that's the model, right? And that's all you really need to know in your head to say, what is a stack? It's a stack of things. It's a list of things where the first thing that goes in, the last thing that goes in is the first one to come off. Likewise, the last one to go in, the first one to go in is the last one to come off. Okay? Sometimes you'll see it written as either LIFO, last in, first out, or FILO, first in, last out. Same thing, right? Okay? So if we wanted to eat these pancakes, unlike normal humans, right? We would take this, we would eat this one, and then we'd eat this one, then we'd eat this one, then we'd do this one in a first in or last in, first out method. Okay? All right. Turns out that model is pretty powerful. Okay? We have already built classes in this class that actually can very easily become stacks. Okay? If you had a dynamic array or any array like this, okay? Here's how the analogy works. You start filling up this array. Let's say you have a value 2, and you put it in the array here. Then you put another value in, and you put it in here. This is now the end of the array, okay? And you put another one in here, 7. And you put another one in here, 6, right? This is, you always append the array. You don't put like 2 and then 3 before it and then set in the dynamic array, okay? The first value you take off is going to be the 6. In fact, the only value you're allowed to take off is the 6. Right? If you're going to take a value off, it's going to be this one. Then if you're going to take another value off, it's going to be this one. You're not allowed to look at these other values. Okay? That's part of the idea of using this stack. And it turns out you don't need to see any of those other values. When we put things onto the stack, we call that a push. In other words, you're pushing it onto the stack. So if I was to say push 7, I would put a 7 in like that. When you take things off of a stack, it's called to pop. That means to take it off like you're popping it off the top of the stack, right? And by the way, this is what's called the top of the stack. Kind of like a head in a linked list. We'll get to what that a linked list version in a second. Push 7. If we were to do pop right now, right, we would have to have some variable that gets popped. So let's say int a equals pop. And what does a now equal? A equals 7, and there's one less thing on the stack. Okay? Sometimes you will have a function that just peaks at the top value but doesn't give it to you. Okay? To peak at the top value, you actually just type top. Right? So if you said a equals top, that would also, in this case, that would give you 3, but 3 would remain on the stack. Okay? All right. Questions on that model so far? Yeah, Margaret.
So are stacks like lists and that you can just always push things onto that?
Exactly. It is simply a list, and it's a list that has a couple of invariants. One of those invariants is you can only put things at the one end, at the top, and you can only take, the other invariant is you can only take things off that end. You're not allowed to look any farther down the stack for this model, if it's just a stack-based model. Okay? That's the thing. Let's look at how we do a linked list version of a stack. All right. If this is 6 and 2 and 4, right? This is our head, and it's a singly linked list. Right? That's our head. Okay. If we want to push onto this list, say we're going to push, I don't know, 7 onto this one. All right, where do you think it should go? What do you think? Yeah. Right here? Okay, so some people, so you think it's there. How many people think it should go over here? A couple people? Why did you say this? Why did you say it should be prepended?
Because then you'll change the head to there, and then you'll get
Yeah, you do it. You'll change the head to what you put it in there, and then you don't have to walk all the way down the end to find that value. Remember how in a stack we always want the last one we put on to be the first one we take off. If you've only got the head, now if you kept the tail pointer, okay, you could probably do it that way if you kept a tail pointer. But in a singly linked list, we normally just keep the head. It doesn't matter. But in this case, yeah, if we want to push 7, what we'll do is we will create another node in front called just like the new node in front, and then move our head to here, right? That's how we would push on. And then to pop, we would say A equals pop, like that. Right? All we do is take it off here and change the head to point to there. And that's it. Okay? We already have functions that will do exactly this. The lab today and tomorrow, you'll see a function, you'll see a class that I've called stack. Okay? It's actually called stack. And it has 3 functions in it. It probably should have 4. There's also, I forgot to put this in the class that we had. There's also a function generally that says is empty. In other words, if the stack has no values in it, okay, then it would be empty. Okay? If you try to pop off a stack that's empty, you should get an assertion error that should say the stack is empty, right? If I had built it in, and you certainly could for the lab if you wanted to, you could build in an is empty, which just checks and sees if there's no values in it or not. If it's empty and you try to pop from it, it's called a stack underflow. If you've gotten to the end of the stack and you don't have some sort of dynamic memory, and you try to push onto a stack that has no more memory available, that's called a stack overflow, which you might have heard about before. Okay? So anyway, that's how we build this. So really, you'll look at the stack class, and there'll be a push method, and a pop method, and a top method, and there should have been an isEmpty method. But those are there should be an isEmpty. But that's it. That's all you have to do for a stack. And it's just a list. There's nothing else fancy about it. It's just a list that has those functions in it. Push, pop, and top, and possibly isEmpty. Okay? That's all there is to it. Questions on this, what a stack is at this point? With this class, and you'll see this in the lab, with this stack class, if you want to create a stack, an empty stack, you just type stack s, or stack lowercase stack, or something like that, right? And that will actually create an empty stack that you can now push onto and pop off of. How would you do it? You'd say lowercase stack dot push 7, or something like that. Okay? Yeah, Margaret.
Wait, so is an empty stack pointing to no?
Depends how you define it. And by the way, I don't care how it's defined. And this is one of the things that we got to get across is there's the way we define these data structures, we don't actually care what happens under the covers. Like, we don't care, right? All we care about is that we can push onto it and pop off of it and do the top and figure out if it's empty. Other than that, it doesn't matter. In a linked list, sure, you might have just an empty stack with point to null. Sure. Yep, because there's no values on it. However you define it, doesn't actually matter to the idea of a stack. You got to separate what a stack is versus how it's built. Okay? All right. Questions on that? Okay, good. All right. So what can we use stacks for? And by the way, why have we seen anything in this class so far that might be stack-based? Say about 15 minutes ago. Yeah. DC is DC is definitely stack-based. How about before that? Anything before that we talked about? Yeah. The maze that we're doing can be stack-based. Sure. How did I say one of the ways we were going to do the maze? We check every direction we can do it with a stack, absolutely. Yes? There you go. Recursion, exactly. Recursion is the way, is a stack-based operation. Your operating system sets aside a portion of memory called the stack, as it turns out. Okay? They're not very clever in that sense, I suppose, but that's what it is. It's an area of memory that you can push values onto and you can pop values off of. And whenever you call a function, okay, all the parameters of that function are basically stored on the stack. Okay? And then when you come back from that function, you replace all the values that you had stored, and you end up continuing where you left off. Here's why we use a stack for that. Okay? Let me do the stack up and down. Sometimes I'll do the stack this way, and sometimes I'll do it up and down. It really doesn't matter. Just know that if it's a regular array, it would be side to side. Let's say here's your stack. So I'm my first function, main. Right? And in main, I call some function, I don't know, function A. Right? What happens when main calls function A is all the stuff about main gets stored on the stack. All the little, if there was a variable here, int A, if there were some other things, right? That would be stored on the stack. And then let's say function A calls function B. Right? Well, what happens in function A is now we've got the stack here. Now function A's stuff goes there, and function B happens. And then the same thing would happen if function B called some other function. Right? And it just keeps building up like this. When function B returns to function A, the stuff that's on the stack gets popped off and replaces the values that need to be replaced because function B could have trashed them somehow. Right? So that would get undone. And notice we took the last one, not the first one. We don't pop off main. We go to the last one that it came from. Right? Function A, and then function A returns, and we pop off main like that. So it's a very much a stack-based idea. You keep pushing things on, and you pop them off when you get done. And it's kind of like, you're going down deeper into levels and then popping off one by one in the reverse order. Okay? Does that make sense? I hope. All right. So that's one of the big things they can do. And stacks are so important that computer architectures almost always have, at their very basic architectural instruction level, functions to push and pop onto various places in memory, because it's such a basic function that's so necessary for things like function calls in programming languages. Okay? All right. OK, so that's the basics of stacks. What other things are possible with stacks? Well, let's go through. What I'm not going to do today is bombard you with lots and lots of code. We're going to talk about how you might use a stack to do stuff. Okay? The code part will come during assignments and things, but I want you to get the idea of what we might use stacks for. Okay? All right. You know when you're in Emacs or some other editor and you've got all these curly braces all over the place, right? And you want to know if you've got them in the right order and you need another one or whatever, and you type, I don't even know what the command is, but you type a command here and it highlights the other curly brace that matches up with it. You know how you do that? Well, we can figure out if a set of program or a set of code is actually has balanced parentheses and curly braces and things simply with using a stack. Okay? So if we want to find out if they are balanced, we would do the following. Let me give you an example instead of writing this whole algorithm down. Let me give you the actual example. So let's say we have this piece of code, and this is not a code that you have to memorize. This is just something I'm making up, right? If a pointer some member x equals 2, then curly bracket C out 2. Right? OK. How do we figure out if we've got enough, if we've got the properly balanced parentheses and brackets and things? Well, we can use a stack. OK? So let's say we have this stack here. Here's how it works. We go along the string here. Let's say we have this as this is going to be some long string, right? And we go along and we look at each character. And when we get to a left parenthesis or a bracket or brace, we push it on the stack. Okay? So let's go along. We ignore, we get a left parenthesis. We push it right on the stack. There's what our stack looks like right now. Okay? We go along, we ignore. Oh, we get to this bracket here. That's a left bracket as well. We push it on the stack. Okay? We ignore x. We get to this bracket, which is a right bracket. At right brackets, we've got to do a comparison and see if we've got a corresponding left bracket. Right? Well, guess what? That happens to be on the top of the stack. So when we get to that right right brace like that, we pop whatever's on the stack, okay? And then we compare and we see, is the type of this left one the same as the type of this right one? They're both brackets, so yes, we're good to go. Okay, and we had popped this off. Keep going along, ignore. We get to a right parenthesis. Right? Well, we get to a right parenthesis, and we say, oh, well, let's pop the stack and compare. And we pop off the left parenthesis, we compare. It actually is equal to a parenthesis, so we're good. We get to this left brace. Exactly the same pattern, right? We push the left brace on. Okay? And then we keep going along, ignore until we get to that right brace. We get to a right brace. We pop off what's on the stack. Right? And we check and see, yes, it's indeed it compares, so we're good to go. And then we're done. And what's the last thing we have to check? Any idea? Yeah. Is the stack empty? Because if the stack's not empty, that means we have one extra guy. Like let's say I did all this and then I threw a parenthesis over here, right? A left parenthesis, right? If I threw that left parenthesis on there, it would then push it on here. And then we get to the end and be like, well, the stack's not empty, so we must have something wrong. Okay, and that's what's wrong. If it had been a right parenthesis, let's say I'd thrown a right parenthesis over there, we would have tried to pop off the stack and it would have already been empty. So we're going to cause an error, and we're going to say, oh, that must mean that our stack, we don't have balanced brackets. Okay? You guys get the idea of what's going on with this stuff? Yeah? All right. So that one's a relatively easy example. Now, earlier somebody said, hey, that DC calculator thing probably used a stack. Well, it actually certainly did. Okay? If you want to evaluate reverse Polish notation or postfix notation, we can use a stack. Okay? Let's see how we might do that. Okay? Here's an example. 6, 5, 2, 3 plus 8 times plus 3 plus times. Ooh, that looks like a long one, right? All right. Here's what you do with this. Okay? If you want to evaluate that, you set up an empty stack. Okay? You set up an empty stack. Now, whenever you get to a number, you push that number onto the stack. Whenever you get to an operator, you pop the top two values off the stack and apply that operator to those two values, and then push the result back on. Let me show you what I mean. 6, 5, 2, 3. We get 6, 5, 2, and 3. 6, 5, 2, 3. We're going to push that, push that, push that, push that. We get to a plus. We say, oh, it's an operator. We'd better pop the top two values off, 3 and 2, and then apply the plus to them. And that gives us 5. And we put the 5 back on the stack. So we have now popped the stack here, popped those two values off, done the operation, and then pushed the 5 back on there. Now we're left with 5 and 5. Okay? Then we get to, let's see, we did the plus. Then we get to an 8. What do you do with numbers? You push them on the stack. Okay? Then we get a times. For the times, we say pop the two values, 8 and 5, multiply them together, and we get 40. So you pop these two values off. You multiply and you get 40. You push the 40 back on. Let's see. Then we have a plus. So same thing. The plus says 40 and 5 come off. You add them because of the plus, and you get 45. You push the 45 back on the stack. Okay? Right? Then we get the 3. We push the 3. Then we get another plus. So we get 3. We get the plus. We pop the two values, 45 and 3. Pop, pop. Add them together. We get 48. Push the 48. And then finally, we get a times. And that times says, do this on the previous two values. 48 times 6 happens to be what? 288 or something? 288. Pop the two values, multiply them, 288. After this is all done, whatever's left on the stack is your answer. Not bad, huh? It's actually a pretty simple way to do this calculation. All you need is this stack. No need to worry about any other like order of operations or parentheses or anything like that. Just boom, run it right through the stack. Very fast, very efficient. Okay, questions on that? Yeah.
What would happen if you don't put in enough numbers or operators?
Good question. So let's say that we had left off this end star here. We would have been left with, I think, 6 and 48. Well, that's what the last value would be. So your result at this point is 48. Now you can do the times and it'll give you it'll give you the other thing. But you can keep pushing values on here until you get to the end. It doesn't really care. I think if you want to do it, if you want to make it so, this has to be to equal one number, then you'd have to make sure it equal that. But most of the time, it doesn't actually matter. Whatever's the top is the last value calculated. Yeah.
Is there a way to see if there are multiple values in the stack, or do you only look at the top of the one?
Good question. You can only look at the top of the stack, and in general, you can only look at like if it's empty or not. Like that's kind of the stack model. I mean, if you wanted to have like a stack plus sort of thing, you could have it so that it counts the number of members in the stack. That's not part of the stack implementation, but you could do that if you wanted to. Yeah, good question. All right. Anything else on this one? Okay. All right. So, you guys ready for the last one? This one's the one that I messed up on earlier. So, please keep an eye on me and correct me when I'm wrong. Here's what we're going to do now. So we have, let's say we go and we build our little reverse Polish notation calculator. And it's really simple. And we do that and we go and we want to give it to people. And we want to say, here's your RPN calculator. And they say, you're crazy. When I was in like 3rd grade, I didn't learn RPN notation. I learned regular old infix notation with parentheses and with order of operations and all that. I want your calculator to work for that. And then you say, oh, well, OK. Do we scrap the calculator that we just built, or do we figure out another way to do it better? Well, I think the answer is let's figure out a better way let's figure out how to use the code we already created to do that. What might we do? Let's say we had the following. Regular old math notation, except it's not going to be numbers, it's going to be letters. Maybe this is what screwed me up earlier. A plus B times C plus, in parentheses, D times E plus F, end parentheses, times G. Whew. All right. Is there a way to convert that into postfix notation? Sure there is. I mean, we can certainly do it, right? Turns out you can do it with a single stack. Pretty cool. Here's what the answer is, by the way. The answer is A, B, C times plus D, E times F plus G times plus. Whew. All right. So we have rearranged this. Taken out the parentheses. You don't need any parentheses, right? And we've had the symbols like this. And if you go through this in a reverse Polish notation calculator, you should come up with the answer that you should get this if you know your order of operations. So our little program does need to know order of operations when we do this. And by the way, again, what we're trying to do, convert this string into this string. OK? We got that? I think that confused some people earlier, too. I did all this, and they're like, I don't even know what we're doing. Halfway through this. What are we actually doing? OK, we're converting this into this so that we can use our other calculator. OK? All right. Instead of writing down all the rules, let's talk about the rules as we go along. OK, before I wrote down all the rules, and that didn't seem to work well here. Here's what I'll do. Start with an empty stack, OK, as you normally do. The way this works is you read values from the string that you're starting with, okay? And they become part of the string you want if they are just variables. Okay, so like A, all we need to do is write down A, because we hit an A, and we write down A. The numbers in this case don't actually go on the stack. It's the operators that end up going on a stack. Okay? So you do this. You say, OK, we've got A. And I'll put the answer down here, and hopefully it'll match up. Okay? We do it. We get to an operator. Well, look, it's going to have to come after this B somewhere. We don't know where yet, but it's going to have to come. So we've got to push the operators. Operators get pushed onto the stack, like that. Okay? So we've got A and then plus. All right, we get to a letter. What do? Move it down. OK, so we got B. Now what we do is we get to another operator. Instead of just pushing that operator on here, we need to know a little bit about order of operations. And here's what the rule is. The rule is, if you get an operator, pop any operations off here that are not lower priority than that operator. Okay? So we've got a star or a times. Is it lower priority? Is plus lower priority? Leave it. Push the other value. Okay? So we're going to get to the star. We're going to say, OK, because the plus is lower, okay, we are going to leave it, and then we're going to push the star. OK, like that. What do we do when we get to the C? Put it down here. OK? All right. Now we get to a plus. We take the plus, and we look at the values on the top. We can only look at the top value at a time. OK. Is the times lower priority? No. So we pop it off, and we write it down. OK? We've still got the plus we're working on, though. Is this plus lower priority than a plus? No, it's equal, but it's not lower. So because it's not lower, you pop it off, and you write it down. And then the plus that's left, right, we push onto the stack. OK? So far, so good? Everybody kind of gets what's going on? All right. Then we get a left parenthesis. OK? A left parenthesis just goes on the stack. In other words, it goes on the stack, and everything below it is actually less priority. I mean, a higher priority than a parenthesis. So we get to the parenthesis, and we say, all right, it's got to go on the stack. We got the plus already. We got the parenthesis. OK? Later, this is actually going to, you only remove this if you get to a right parenthesis. And why is that the case? Let's think about what's going on here. When you're doing all the stuff inside parentheses, all that has to happen first, right? By the time you get to here, you'd better be done with everything inside of it. Right? That hopefully makes sense. All right. So you get to the left parenthesis, and you push it on here. OK, then what do you do with the D? Write it down. You get to the star. And you go on here, and you say, all right, is the left parenthesis lower priority? It's not. When it's on here, left parenthesis stays. OK? So you don't do anything with it, but you push the star. OK? So we did that. We did that. We get to the E. We write down the E. We get to the plus. We say, hey, is the star lower priority or is star lower priority than the plus? No. So we pop it and write it down. OK? Parentheses only come off with a right parenthesis. OK? So we've still got that plus. We better push it on here, like that. OK? So we did the plus. We get to the F. We write it down. We get to the right parenthesis. Now, right parentheses say pop everything off the stack until you get to that left parenthesis. So everything that's left had better happen before that parenthesis ends. That makes sense, right? So we pop off the plus, and we write it down. And then we're going to pop off the left parenthesis, right? But we don't write it down, because there's no parentheses in this thing. We just take it off the stack. OK? And then we're good to go. We get to the times. OK? Now we're at the times. And we say, all right, go back here, look at the stack, and say, is plus lower priority? It is, so we leave it. Get to the one with the lower priority and leave it. Push the star on there. Push the star. All right, then we get to the G. We write it down. And then we've got two symbols left on the stack at the end. We're done reading our input. We've got two symbols left on the stack. We just pop them and write them down. The star gets written down, then the plus gets written down. plus. Okay? You see it now. Do you see how we've gone through this string and turned it into this one? Well, this one. Right? That's just using a few simple rules and one stack. Okay? Any questions on that? No questions on that, huh? Yes? Very good question. What's the precedence between division and multiplication? They're equal, right? Yeah, you guys remember from like like algebra class or whatever, like sixth grade, right? PEMDAS, right? They always teach it like this. It's a power, or what is it? Parentheses, exponentation, multiplication, division, addition, subtraction, right? I don't know if you've seen this one before. But what they never tell you is that these two should be like, it should be like that, right? Because multiplication and division have the same precedence, right? And addition and subtraction have the same, and it goes left to right. They never really talk about it being like, I mean, I'm sure they do, but like all the kids are like, oh, it's PEMDAS, right? Well, they don't actually, I don't think they stress that quite enough for some of these things. But anyway, to answer your question, all you do is you say, if it's the same, you just make them the same priority as their corresponding type. So subtraction and division work for that. What doesn't work is no, it actually does work. As it turns out, it does work. You just need to know that if you have A, B divided, right? Let's say it's divided by, you need to go A divided by B. Like that's, it's just like, it's before we did A plus B. I mean, you got to remember to do it in that order. It does work out fine. What doesn't work out is if you just have a negative number, right? So let's say we started with like -2, 3 plus. Well, the whatever it's doing, the parsing of this, it gets to the negative and it says, pop the stack and give me 2 values, right? And it has no idea. So you have to, when you do negatives with this notation, you have to say, oh, OK, I have to figure out if this works. There's a couple ways of doing it. When you see something that doesn't have a corresponding part to it, you can make it a different symbol on the stack and know that it's a different symbol. Or maybe you could do something, if you see negative numbers, you'll go through and replace it with like 0 first or something like that. But there's ways of dealing with it. You can also do things like powers of things. And there's some that the ones that it doesn't work with are the ones where the other ones that it doesn't work with are the ones where you do have to do them in a different order. I'm trying to think of a good example. Off the top of my head, I don't know a good example. But there are some cases where there's special cases. So DC takes care of all that. It knows it. I think you can do things like absolute values and things in DC. But that's the bottom line. OK, so where does that leave us? So we talked about the idea of what a stack is, just a list. It's just a list that you can only pop or push onto the one end. You pick the end, but it's got to be the same end each time, such that we follow this invariant that it's first in, last out, or last in, first out, right? We have to follow that. And you can also have a top, and you can have an is empty, and that's about it. OK, very powerful data structure, but also very relatively simple. That's kind of why we start with it. OK, next time we'll talk about queues, which if you're from like Great Britain, you know all about queues, right? In the US, people are like, a queue, what's a queue, right? Everybody knows what a queue is in like the Commonwealth countries, right? But you talk about queue, like a queue at a supermarket. It's like the line you get into, right? Right? Well, what happens with a queue? Right? The first one in is the first one out in a queue. Okay? It would kind of be bad if supermarket lines were stack-based, right? Because like the first guy gets in line, and if anybody else gets in after him, he's never going, right? Like until everybody goes, and that would be bad. Yeah, that would be pretty terrible. But queues are kind of the other way around, where you push things on one end and you pop them off the other end. Okay? We call them Q and DQ on the other end. And by the way, Q is not just one letter. Q, U, E, U, E, right? So that's what you do there. But by the way, speaking about queues, I should talk about this next week, but on Wednesday. But speaking of queues, you know how you go to the supermarket and there's like 10 different lines, and everybody lines up, and it's always this like, which line should I get into, right? And it's annoying, right? Because I always pick the wrong one. And I mean, almost always, but who knows? A better model is the one that some stores do, like some of the bigger box stores and some Targets and things do it, where you have one line and all the different ones feed off. So the first guy in whatever line ends up going to whatever open register is next. That's a much better way of doing it. They should move all supermarkets into that method. But it's what? They should make the other model, yeah, they should make it illegal, right, to do it the other way. But anyway, OK. I think we're going to end a little early because I didn't screw up this. So that's it. Any last minute questions? OK, see you guys Wednesday. Or at office hours or labs today.